Very good evening, Ranju. Please do confirm once that you can see me. You can hear me as well as you can see this presentation. After that, we can start. If everything is fine, then let us start. So, Okay, so let us start. So, very good evening, everyone. Today, I will be taking your live interactive session on the course Statistical Learning for Reliability Analysis. Okay, my name is Ambuj. I am research scholar at Agriculture and Food Engineering Department from IIT Kharagpur, and we shall see everything here. Okay. Regarding your week 4, with reference to the NPTEL course, Statistical Learning for Reliability Analysis. In the previous weeks, we have seen a lot of concepts based on probability as well as the distribution. Now we'll be solving some of the questions as well. We'll be solving some of the things based on the concepts related to sampling. Okay, sampling, mean, mode, median, as well as which type of distribution, which type of sample follows, and what are the different parameters which we have to take into account in order to calculate sample mean statistics, various statistical parameters that we will see in this particular lecture. Okay. So this is with reference to week 4 of this particular NPTEL course, Statistical Learning for Reliability Analysis. Okay. It is designed to this particular module we have designed for delivering foundational and advanced concepts in sampling theory. Okay. First of all, statistical learning and reliability distinguishes the fundamental between the deterministic properties of unobserved population and the stochastic properties of sample statistics. Okay. See, there are two different terms. First one is population, another one is sample. Okay. One term is population, another term is sample. Okay. So, in case of statistics or in case of advanced machine learning or even simple concept of machine learning, in all those particular cases, it is very, very important for you to understand what is population, what is sample. See, first of all, you have to understand general experimentation first. Okay. In case of your general experimentation, what happens that an experiment, suppose an example of experiment is, say for example, you are tracking the yield of a particular crop, yield of a particular crop. Okay. Or let us say a more relevant example to your field, you are predicting the faulty items, okay, from the assembly line. Okay, there is an assembly line. It is having different items which are manufactured, okay, through various processes operating in series or parallel. Now you have to inspect this assembly line. Okay. So in this assembly line, suppose 1,000 number of products are being manufactured every 1 hour. Okay. So if you want to predict that what is the exact percentage of samples which are having any possible defects, okay, which are having any possible defects. So in order to predict this particular case or scenario, what you will do, you will take, suppose you will perform an experiment in which you will say, suppose select a sample, a particular sample. For example, this 1,000 is the entire population. Okay, this 1,000 is the entire population, and from this 1,000 population, for identifying the percentage of possible defective items, you will select, say, suppose a sample of 100 items. So you will pick a random sample of 100 items. From 100 items, what you will do, you will suppose take a particular sample. Okay. This one is your sample. So the size of sample is 100. The sample, the population size is 1,000. Okay, this one is corresponding to the population. Why you have reduced the number of items from 1000 to 100? Because you have to identify in a very considerable amount of time, in a practical amount of time. You cannot manually inspect 1000 items in entirety. Okay. You will be just observing a particular part of the sample, supposedly maybe 100 items. Okay. A percentage of the items you will be inspecting, and on the basis of those particular items, whether they are defective or non-defective, you will be claiming that this much percentage or this much amount of items are defective from the particular manufacturing line. Okay, this is the general idea. So what you will do, you will manually inspect or apply some of the sensing, or maybe through some of the various topographical features you will identify. Okay, or if not, what you can do, you can use some sensing equipment. Okay, after that you shall be in a position to declare what is the exact percentage of samples are defective in case of your sample of 1000 items, of 100 items. Okay. Then what you will try to do, you will try to predict that exactly how much variation is there. Means, for example, you found that out of 100 items, 90 are good, in a good condition, and 10 are defective. Okay, 10 are defective. Now you shall be predicting that what is the percentage of defects or defective items in the entire population. Means, in 1000 items which have just came from the assembly line, what is the exact percentage of items, percentage of defective items which would be there present in the entire population of 1000 samples. Okay, so it is regarding your estimation of population mean, estimation of population mean from sample. Okay, or you can say that estimation of test statistic, population test statistic from just 1 second, guys. I think my system has just gone into hanging mode. Sorry for the interruption. My system just got hanged. I'll be sharing my screen once again. Yeah. So I hope that whatever I wrote, it just went away. I'll write once again. Yeah. So I was talking about the estimation of population statistics. Say suppose a sample is having population size of 1000, and on the basis of this particular whole population size, you have selected a sample of size 100. Out of the size of 100, you have came to find out that 90 number of pieces or items in an assembly line are good and 10 are defective. Okay. So this is your inference based on this particular test statistic. Okay. On the basis of a test statistic, you have found you have first taken a sample from a large population, and then you have found out that what is the exact number of good and bad samples from a sample size of 100. Okay. When the entire population is having size of, say, suppose 1000. Okay. This is regarding the population. This is regarding the sample. Okay. This is regarding good, means how many number of items are good, and this is regarding bad, means how many number of items are having a bad ratio. Okay. So now you try to see that from this first of all, why you have taken out the sample. You have taken out the sample because you, you were not in a position to check entire 1000 items, and you were not able to check 1000 items in a delineated amount of time, in a restricted amount of time. Okay. So entire 1000 samples you shall not be in a position to see. So that is why you have taken 100 items. Okay. 100 items out separately as a sample. And you have found out that 10 number of pieces are exactly defective in my sample size. Now you have to estimate the defective number of items in my entire population. This is my problem statement. Okay. Why I will estimate for my population so that I can give a idea in my manual, that is my manufacturing document, in my product manual, that how many number of items may be defective to whatever line I am supplying. Maybe it's a B2C, means business to directly customer type of business. Then I'll be saying that this many number of items are defective. I am already claiming it. Okay. And if anything is found to be defective, we will return and reissue one another end. Okay. This might be one thing. Another thing, maybe if it's a B2B business, okay. If you are, for example, supplying ball bearings to an aircraft engine manufacturing unit, okay. So in that also you will be saying that, sir, this many number of items are may be found to be defective. Okay. So that that particular items will replace. So now the question arises, how you will estimate this particular population defective items, means in the entire population, what is the exact number of defective items from your sample statistics, from your sample analysis? How you will do it? You can claim that, sir, in this particular case, 10% items are defective. So in the entire population, 10% items will be defective. You may directly claim and say to me that I have found that 10% number of items are defective in my sample. So 10% would be effective in my population. Okay. You can say like this. Okay. So you can infer this particular information, but after rigorous experimentation by various statisticians, it has been found out that things that do not behave linearly like this. Because, see, manufacturing or any experimentation is a complex process. Okay, it does not generally behave linearly. The number of defective items which would be there, they won't be constant. The machine parts which are currently in friction process, heat is getting generated. Okay, they are subjugated to friction also. So they won't be manufacturing same quality of products during the entire period of operation. So maybe in the first hour, what will they will manufacture? They will manufacture good products, means less number of defective periods. After 2 hours, 3 hours, that same machine will manufacture more number of defective products, or it can be vice versa also. Means during the first hour, the friction was so high, the bearing temperature, the hydraulic oil temperature, and every other parameter was such that the entire machine got overheated, and after 1 hour cooling, it got back on its own, and the quality improved. So that can also be a case. Okay, just one second, just one second, guys. Yeah. So you have to estimate the population statistic on the basis of sample statistic. Okay. हाँ सनी मैं क्लास ले रहा हूँ मैं बाद में कर Yeah. So you have to estimate this particular population statistic on the basis of sample statistic. So that is the particular challenge which you have to fulfill. Okay. So after general experimentation, it has been found out that you cannot directly estimate. Okay. Directly estimation is not a valid method. Okay. So the real-time processes are a bit complex. Okay, some conditions are there. So that is why we generally go for these particular methods. Okay, some statistics, standard test statistic have been derived, where to apply, which one to apply. That particular should be clear to you. There are various parameters on the basis of that only it is decided. Okay. So that particular information is very, very essential. Why it is essential and where to use it, that I already told you. Okay. So after going through this particular course, there is a particular department in almost all of the manufacturing companies or multinational companies or any type of company, that is quality control. So in that particular department, which is quality control, this particular concept of test statistic as well as how to maintain the particular quality. Maybe it is of food product, maybe it is of manufacturing product, maybe it is of mechanical product or any product that has to be controlled. There are strict regulations regarding that. Means that a particular concentration of bacteria in your milk product or in your fruit juice should be less than a particular threshold. Okay, so that particular uh, that particular condition has to be met. for all the products which are manufactured in a particular batch. So in that particular scenarios, it becomes very, very important that you control the quality. And how you can control the quality when you will be knowing that how to select the sample out of my entire assembly line manufacturing process. If when you will be in a position to select the sample, then you will be performing the experimentation on the samples. And after performing the experimentation, you shall be in a position to control the quality. How many number of products you have to retain, how many number of products you have to manufacture, and how many number of products you shall be in a position to sell, or they should be coming out of your factory or board. Yeah. So this is the general idea that why we are studying this particular course and why we are studying this particular concept. Okay. So this is regarding this particular concept. Okay. So now you try to see the population parameters versus your sample statistics. Statistical learning is in reliability distinguishes fundamentally between deterministic properties of an unobserved population and stochastic properties of sample statistics. So population parameters are fixed. Okay. Population parameters are generally fixed. Why? Because the entire goods which are getting manufactured in a particular assembly line, they will be fixed only. Okay. So population parameters are fixed, typically unknown constants defining the underlying probability distribution of entire universe of components or products processes under the study. First parameter is population mean. Population mean, the expected value representing the true long-term average or mean time to failure. Okay. So that is nothing but expected value of x or mu, that is a definite integral minus infinity to plus infinity x into f of x, where fx is the probability distribution function. Okay. Population variance is there, the true measure of dispersion around the central tendency. Okay, that is sigma square. Okay, variance of x equal to expected value of x minus mu whole square, that is expected value of x square minus mu square. Okay. Population proportion. True proportion of items satisfying a particular reliability criteria may be different. Okay, maybe true defect rate. That is already given to you. Now, sample statistics. Okay. Sample statistics are functions calculated from observed sample data. Sample data means x1, x2, x3, plus and so on up to xn. Because the sample consists of random variables, any statistic is itself a random variable governed by probability distribution called its sampling distributions. Means the distribution in which the particular sample is behaving. Okay. So for your sample mean, it is nothing but x bar. X bar is 1 upon n summation I equal to 1 to n xi. Yeah. Sample variance s square is 1 upon n minus 1 summation I equal to 1 to n xi minus x bar square. Sample proportion p cap is nothing but x bar. X follows a binomial distribution with sample size n and probability p of which is the positive probability of opening of an event. Then sampling distribution of the mean is x bar and central limit theorem. You just try to see here. Sampling distribution of x bar, okay, mean characterizes the statistical behavior of the sample mean computed across repeated independent rows of size n from a population with mean mu, finite variances sigma square. Mathematical derivations are there. Okay. For example, expected value, what expected value to be following? Okay. The sample would be following expected value of the same, means mean will become same. Okay. X bar is an estimator, unbiased estimator of mean. Mean was regarding your population. Okay. And X bar is regarding your sample. Variance and standard error, that is for the sample sigma square divided by n. Standard error x bar is represented by sigma over root of n. Okay. As n will be approaching infinity, standard error will be approaching zero. Okay. Central limit theorem, it says that when x1, x2, and xn be random variables with mean mu and finite variance sigma square, where sigma square is greater than 0. As n will be approaching to infinity, the standardized variable Zn converges in distribution to the standard normal distribution n with mean mu as 0 and standard deviation sigma as 1. You know. So Zn will be nothing but x bar minus mu divided by sigma over root n. Okay. So consecutively, for sufficiently large sample sizes for n greater than equal to 30, the sampling distribution is approximated. Likewise, this means mean is taken mu and variance is taken as sigma square divided by n. For less than 30, okay, less than 30, you can go with directly with this. Okay. You can take mean as 0 and variance as 1. While for n greater than equal to 30, you can take mean as mu and variance as sigma square divided by. For example, see here, a batch of electronic components has a population mean lifetime mu as 800 hours, standard deviation sigma is 120 hours. For a random sample of small n equal to 36 components, okay, compute the probability that mean lifetime x bar, which is of sample mean lifetime x bar exceeds 120 hours. You have to just compute that sample mean lifetime x bar exceeds 820 hours. So mu has been given as 800, sigma is given as 120, n is given as 36. Standard error SE will be nothing but sigma over root of n. Okay. So sigma over root of n, 120 divided by root of n, that is root of 36. Root of 36 is 6. So it will come as 20. Z score if you will try to calculate. Okay, Z score if you will try to calculate, it is nothing but x bar minus mu divided by standard error, sigma over root error. Okay. So x bar minus mu, x bar is 820. Mu already has been given mu as 800 hours. Okay. 800 divided by sigma over root n. Sigma over root n we have calculated. Sigma is 120. Root n we have already divided it. That is 20. So it is coming as 1. Now you have to check for the probability that z is greater than 1.0. Okay. That will be equal to nothing but the probability z greater than 1.0 is nothing but the probability 1 minus probability z is less than equal to 1.0. So for calculating this, you have to use the normal table, standard normal table for z distribution, in which you will get this particular z value as 0.8413. Okay. So that would be nothing but 1 minus 0.8413. That is 0.1587. Okay, if you are unable to see Z table, I will show you. This is Z distribution table. Okay. In case of your Z distribution table, it is representing the area to the left of Z score. Okay. One particular parameter alpha should also be given to you in this particular case. Okay, alpha should be also given to you. Then you shall be in a position to calculate. This is how the Z distribution looks. Okay. This will be certainly provided to you in the examination. Okay. This will be certainly provided to you in the examination, and you have to just see the particular value. Okay. That alpha I haven't mentioned here. I'll try to show you with another example. Okay. Directly this particular value you will be able to calculate. Okay. Sir, standard deviation and standard error both are same. No, standard deviation is some other thing. Standard deviation is nothing but your sigma, this particular way. And sigma over root n is your standard error. So both are very different. They are not the same.
But sigma by square root n is the standard error.
Yeah.
But our z value you need to compute x minus mu by sigma.
Mhm. X minus mu by sigma over root
Sigma.
n, not divided by sigma here. Divided by standard error. I have divided by standard error. Okay. It depends on which particular distribution it is there. X bar minus mu divided by sigma also you can do. X bar minus mu divided by sigma over root 1 also you can do. It depends what are the parameters that have been given to you in the question. Okay. You can divide it by sigma also. There is no problem. Based on the entire question, okay, whether it has been already normalized or you need to normalize. Dividing by root n is just normalizing the number. Okay. I hope it is clear to you. Just wait for some more time. I'll be solving some of the questions. Thereby, it will become more clear to you. Sure. Whether you have to divide it by sigma or sigma by beta, okay, it will be clear to you. In this particular condition, it is there for n less than 30. N less than 30, you will have to just go for x bar minus mu divided by sigma. But n greater than equal to 30, here it is 36. So I am assuming it is following a normal distribution with mean mu and variance sigma square divided by n. So that is why I am estimating the standard error and dividing it by standard error. So particular condition is there, whether your n is less than 30 or more than that. That is the case. I hope it is clear to you. Should run that one.
Yeah, got it.
Okay. Yeah. So regarding your sampling distribution of sample variance S square and chi-square distribution. This chi-square distribution is another type of distribution, okay, in which the sample variance formula uses n minus 1 in the denominator to ensure n/c. Okay. Sample variance S square is having this particular formula S square equal to 1 upon n minus 1 summation I equal to 1 to n psi minus x square whole square. Derivation of unbiasedness is also there, and after deriving the whole, you get that it is equal to sigma square. So it's kind of unbiased. Why? Because there is no particular difference found between the sample mean and the population mean. Okay. So this is regarding your expected value of the square. If you want, you can try. Otherwise, there is no particular problem. Yeah, in case of chi-square distribution, it follows a normal. It follows a distribution with mean mu and variance sigma square. The normalized sample variance y follows a chi-square distribution with here n minus 1 degrees of freedom. I have taken this symbol mu. You can find in books. It can be mentioned f also. Okay, in many books, there is a possibility that you will find it written as f. Okay, so both are same things only. Okay. So in this particular case, chi-square with degrees of freedom mu or f. Okay, it will follow. An expected value will come as mu, that is n minus 1. Variance will come as 2f, 2n minus 1. Okay. It will have a asymptotic behavior, okay, positively skewed for small mu from this to n mu to too new as new approaches to interpret. Very easily shall be in a position to solve this or prove this also. Okay. And the test statistic would be nothing but n minus 1 into s square divided by sigma square. That is your chi-square distribution with n minus 1 degrees of freedom. One another distribution is student t distribution is there. Okay. See, conditions are very, very important for you to understand which distribution you have to apply. I'll show you in detail also. But see here, when sigma square is unknown, sample sizes are small, n is less than 30, then you can substitute S for sigma to introduce the additional variability. Okay. So Z, you will try to calculate x ahead minus mu divided by sigma over root n. It is deemed to follow with a normal distribution with variance 0 and sigma square and variance 1. Okay. Y is n minus 1 s square over sigma square, that is chi square n minus 1. So x bar and s square are stochastically independent and are normal sample. So this is another type of proof in which we have tried to relate with two particular distributions, that is chi-square distribution in your this particular one normal distribution. So we have tried to correlate and we have got x bar minus mu divided by s over root n. In case of your standard distribution versus student t distribution, symmetry in center is the particular value, symmetric around mu equal to 0, 1 is symmetric around mu equal to 0 and mu greater than 1. In case of variance, variance of z is equal to 1. Here variance is f over f minus 2 or mu over mu minus 2 for t greater than 1 and for mu greater than 1 for mu greater than 2 this particular variation would be better. Okay, mu over mu minus 2 f over f minus 2. Tail weight is normal tails. Okay, in case of standard normal distribution it is heavier tail or heavier propensity on extreme deviations is there in case of your student e distribution. Okay, for students normal standard normal distribution it's a fixed distribution. Okay, and in case of your student tree distribution this with normality and 0 1. Okay, as mu approaches to infinity. Now f statistic, the ratio of scaled sample variance is defined the f distribution. Okay, F distribution when x1, there are two independent normal distributions, x1 which follows normal distribution with variance with mean mu1 and variance sigma 1 square, and x2 with uh, mean mu2 and variance sigma 2 square. Okay. Sample sizes are n1 and n2, then you try to calculate the F test statistic, that is this particular one. N minus 1 s1 square divided by sigma 1 square divided by n minus 1. Okay. Then n2 minus 1 into s2 square divided by sigma 2 square whole divided by n2 minus 1. Or if you want to remember, s1 square over sigma 1 square and whole divided by s2 square over sigma 2 square. Okay. When mu1 equal to n minus 1, n1 minus 1 is the number of degrees of freedom and mu2 equal to n minus 1 is the denominator degrees of freedom. Numerator degrees of freedom and denominator degrees of freedom. So analytically, if you want to prove the reciprocal property of f distribution, that for critical values of f distribution, you will be getting a particular distribution if it is having degrees of freedom mu1, mu2, it shall be inverse of 1 over degrees of freedom mu2 mu1. Okay, this particular analytically, if you want to prove, then this is the proof which is given here. Then sampling distributions of proportion p hat. Okay, So if it can be X denote the total number of successes conforming units in an independent Bernoulli trials with parameter P. Okay. So it can be a binomial distribution also. Okay. With probability of success as P and sample size as N. Then expected value we have just seen in previous lectures also. It becomes P, whereas becomes P into 1 minus P divided by N. Standard errors becomes P 1 minus P divided by N whole invariant. So in case of a normal distribution approximation criteria is there, okay, Laplace limit theorem is there. Okay. And this particular thing also you can see that uh, this only sample size is only important for you to remember. That if it is n is greater than equal to 30 or n less than equal to 30. If sigma square is unknown and n is less than 30, you go for 20 distribution. Sigma square is known and is greater than equal to 30, you go for Z distribution. Then chi-square distribution is also there. Okay, for single population chi-square with n minus 1 degrees of freedom. So two independent populations, if you want to compare, then you have to go for n1 minus 1 comma n2 minus 1. Okay. Then interfering population proportion, if np is greater than equal to 5 or n into 1 minus p is greater than equal to 5, then you go for normal approximation. In case of your reliability engineering, the sampling distribution of mean x bar and central limit theorem, this once again I have explained with a mean mu variance sigma square over n, standard error sigma over root n. So this is nothing but just a repetition. Okay. Once again, I think it got repeated the same particular example. T statistic already explained to you, chi square explained to me. F statistic explained to me. There is nothing much. Yeah, this marks the end of this particular video. I think it got repeated twice. There were some other things also I wanted to explain. I don't think so it has come. But this is more than sufficient for you regarding this particular week 4. If you understand all of these things, then we shall look into some of the examples. We'll try to solve those. Okay. Yeah. In reliability engineering, we test a batch of small n equal to 50 heat pumps to estimate the fleet's behavior. Is the calculated mean lifetime x bar a random variable or a fixed constant? A part is fixed constant because it is calculated from specific data set. B part is random variable because its value changes with every new sample tested. Fixed constant exactly equal to the population mean mu. Random variable, but only if the sample size small n is less than 30. What should be your opinion? See here, Fuel is derived based on the simple distribution. What is AQL? Mr. Paul, tell me. Yeah, this was the question. In reliability engineering, you test a batch of n equal to 50 heat pumps to estimate the fleet's behavior. Is the calculated sample mean lifetime x bar a random variable or a fixed constant? Your correct option would be that it's a random variable. Okay, it's a random variable. Okay, the population truth mu is your fixed amount. Okay, that is constant. Sample statistic x bar is our uncertain or the fluctuating estimation because for different samples this will come different. Okay, the sample statistic x bar is a uncertain fluctuating estimation of that particular angle, that is your population growth. If you pull a different batch of 50 pumps off the assembly line, x bar will change. Okay. So mu and sigma square is your population parameter. These are fixed. These are unobservable constants that we cannot observe. Okay, because for 1,000 samples or an n number of samples, it is very not very feasible. Okay, and you are going for sample statistics, that is capital X bar and S square. These are the functions of random variables, where X bar is nothing but summation of all the values xi's, which are the random variables, their whole sum and divided by n. Okay. So x bar will be having its own probability distribution. Okay. So a fixed constant, because it is calculated from specific data set, is wrong. Fixed constant exactly equal to the population mean mu is wrong. Okay. Random variable, because its value changes, is very every new sample tested. This is 100% correct. Random variable, but only if the sample size is small and less than 30. No, it will be always a random variable, whether the sample size n is greater than 30 or it is less than 30. So that shall be your answer. Means it would be a random variable because its value changes with every new sample test. Okay, that is the case over here. Now for another example, you try to see this particular case. Historical data shows a component's lifetime has mean mu equal to 800 hours. Standard deviation sigma is equal to 20 hours. For a random sample, small n equal to 36 component, what is the probability that x bar exceeds the 820 hours? Okay. Where to calculate this particular value? Yes. Regarding your query regarding sir, AQL is derived based on the sampling distribution. Is I am right, sir, or anything else? Yes, you are absolutely right. I was not, I was a bit confused regarding whether you are asking for AQL of this particular question or your own. That is why I didn't answer. First of all, I wanted to clarify which AQL you are exactly talking about. AQL in general or acceptance quality limit. It's based on sampling distribution. It shows the chance of accepting or rejecting a batch of items using operating characteristic curve. Yes, is derived based on sampling distribution only. Okay. Sampling distribution will likely show that whether a random sample represents the whole batch or which particular, how likely it is to a random sample will represent the whole batch of the entire products in the assembly line. it keeps uh, the producer's risk or the consumer's risk. Both the risks it will try to uh, just keep under a check. Okay. So various standards ISO 1900 to 2000 or 2000 to 2000, 2026 are there, or different ISO standards are there, ANSI standards are there. They are generally used to determine that which are the reliable products or which are the type of products which we generally have to keep and which are the type of the products which we visit in a particular assembly in or uh, particular different types of products. Okay. Is that the ones? B is coming. Okay, good. Z greater than 1.0.
RAG, AI agents.
So yes, if you have solved it correctly, it's very nice. The rest we'll just try to solve. Okay. See here. Historical data shows a component's lifetime which is having mean mu equal to 800 hours and standard deviation sigma equal to 120 hours for a random sample n equal to 36 components. What is the probability that sample mean x bar exceeds 820 hours? Okay, first of all, you have to calculate the Z statistic. Why we are using this particular formula x bar minus mu divided by sigma over root n? Because the sample size n, which is 36, okay, it is greater than or equal to 30. If it is less than equal to 30, we will be using some another estimate. Okay. If it is there, then we will be directly using x bar minus mu divided by sigma. But since it is greater than 30, greater than equal to 30, we will be using sigma over root. X bar that has been given to you, okay, components lifetime, which is having mean of 800 hours, sigma is given 120, n is given 36, x bar is given what 820 hours. It is x bar minus mu divided by sigma over root n. Okay. So everything has been given to you 820 minus 800. divided by 120 divided by 2 into 36, that is coming 1.0. 1.0, if z, you are getting this particular z, see here, z table is this one. Okay. Z table looks like this. Okay. Standard normal distribution table represents area to the left of z square. But there is one another twist that this particular value, what is being asked in the question, x bar exceeds, means probability that this z is greater than 1.0. So it would be nothing but, since it is giving you the area to the left of the z distribution, you have to calculate the area to the right of the distribution, and the entire area would be equal to 1. So you just subtract this particular z value from 1. Okay. So this particular z at 1 value, if I want to see here, this is the Z distribution table. 1.0 is this particular row. Okay. Let me change the color of pen. Yeah. 1.0 is this particular row. Okay. This particular row. And see, this particular value is 1.0, and this is the value after decimal. Okay. 0.00.001 means this particular row would be corresponding to 1.01. This particular row would be 1.00. This would be 1.01. This would be 1.02. This would be 1.03, plus and so on up to 1.09. Okay. So likewise, you would be getting 0.84134. Okay. 0.84134. This you will subtract from 1, you will get 0.1587. Okay. That would be option number B. So even if individual components are heavily skewed, they follow in exponential decay the average lifetime of the large batch, that is n greater than or equal to 30. It behaves normally only. Means it allows engineers to predict batch rejection rates without knowing in the line of the distribution. Okay. Next problem. You are estimating an average failure time of an expensive jet turbine.
Sir,
Yes, yes. Please.
sir, what is the outcome, sir? We got 0.1587 solution is came.
Mm-hmm. Okay. So,
From this, what I can be concluding,
okay. Okay. This,
this value is greater than, okay, this is a studio, it is available that side,
okay. Okay.
understand, but what I can be conclude, what I can say to management,
Okay. Okay. So, the conclusion which you can make, see, suppose historical data shows components lifetime as a mean 800 hours. Okay. And standard deviation is 120 hours. For a random sample n equal to 36 components, what is the probability that sample mean x bar exceeds 820 hours? So you can conclude that out of 800, out of the entire batch or the population, okay, out of the uh, components, entire performance analysis, okay, 15.87 percentage of components would be performing for less than 800 hours, and 84.13 percentage of components would be performing for greater than 800 hours. For not 800, 820. Just change my statements for 820. Okay. Means you can say that 15.87 percentage of components. Okay. So 15.87 87% of components would be performing for less than 820 hours. Okay. And 84.13% of components would be performing for greater than 850 hours. That is what you can say about the components lifetime. Okay. That is what you can say about the components lifetime from this particular project. Is it clear?
Sir, sorry, sir. Sir, sorry, sir. P of Z is equal to greater than 1. That means probability of, that means it is a 100% 1 means as per
100. Yeah,
probability.
yes, 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 yes.
Yes, that means
Mm,
820 greater than 820 hours is fifteen
uh,
percentage.
yeah, greater than 820 hours is 15%. Yeah,
Less than 820 hours is 85 percentage.
less than 80. What is the probability that sample mean X? Yeah, yeah, yeah. No, 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 no. I don't think so. That shall be the case. Means you want to say that 15.87 percentage would be performing greater than 820 hours, and
Yes, sir.
84.13 percentage would be performing less than 84 means less than 820 hours. That is what you want to say.
Yes, sir.
Okay. Then there is, okay, okay. What is the probability that the sample mean? Okay. I'll just try to explain it with more number of factors involved. Meanwhile, you look to this particular question. I'll try to give you a plausible explanation. Just one second. Give me, I'll plot some of the things. Then it will be some more clarity. Just for the minute, please continue with this question number 3. Okay, try to solve it. I'll give you a proper explanation of that. I understand your confusion. Maybe I also have some spoken something else. I'll just try to explain this. Very good. Yeah, you are estimating the average failure time of an expensive jet turbine. If you quadruple your sample size from small n to 4n, what happens to the standard error of mean? Very simple. Standard error is sigma over root n. Okay. Sigma, suppose it is old. If I am calculating it as sigma old is nothing but sigma over root n. Okay. It is nothing but sigma divided by under root n. Okay. And new state, it is sigma new. It is nothing but from n to 4n I have calculated. So it will be sigma over under root 4n. So it would be nothing but sigma over 2 root n. Okay. Root 4 is 2. So that would be nothing but sigma over root n is sigma old. So that is sigma old divided by 2. Sigma old divided by 2. So which option is this one? Uh, it increases by a factor of 4, it is wrong. It decreases by a factor of 4, it is wrong. It decreases by a factor of 2, this is correct. It remains mathematically unchanged, this is not. Decreases by a factor of 2. Okay. The square root law of reliability testing: to cut your statistical uncertainty in half, you must destroy 4 times as many number of components. This proves the severe diminishing returns of brute force physical testing. So for exactly you, if you want to increase your reliability by 2, okay, you have to destroy as many number of defective components. And that is the case. So this is a very simple question. Okay. Decreases by a factor of 2. That should be the case. It becomes half. That should be the more correct option. Yeah. For a normally distributed component lifetimes with a two variance sigma square, what is the probability distribution? Correctly models the sampling distribution of the scaled sample variance n minus 1 into s square divided by sigma square. Standard normal distribution, students T distribution with n minus 1 degrees of freedom, F distribution with n minus 1 or n degrees of freedom, chi-square distribution with n minus 1 degrees of freedom. This will try to explain or tell me. Very good. Yes. For a normally distributed component lifetimes with a true variance sigma square, what is the probability distribution? It correctly models the sampling distribution of the scale sample variance and minus 1 this is square divided by sigma square. Okay, this is the expression. And when we are talking that it is C. Okay, let's see. Definitely, it shall be a correct. By definition, the sum of independent squared standard normal variables, okay, zi square is a chi-square distribution. This is summation xi minus x bar wholes divided by sigma whole square, that is n minus 1 s square divided by sigma square. Okay. So chi-square with n minus 1 degrees of freedom, that should be my answer. In our practical applications, we use this particular model to model the volatility of manufacturing tolerances. Okay. CNC machines vibrationally increases. It produces highly variable part dimensions. Okay. So chi-square statistically detects the critical loss of precision. Okay. In that particular sensitive scenarios, we can only try to use this particular distribution. This was regarding question number 4. Now there was some question. Sorry,
Sir,
some confusion. Yeah, yeah. Please go ahead.
sir, in this formula is okay, sir, but how we can say it is a reliability translations, sir? This how it will be applicable this formula? Any
How?
example?
Okay, okay. With the help of an example, I'll try to just explain you. Uh, First of all, let me clarify this previous question. I'll just talk about it. There was some confusion in question number 2. Let me solve that first. Then I'll talk about the chi-square distribution practical applicability. I'll talk about. Okay. Just give me some time. The historical data shows components lifetime mean mu is 800 hours. Standard deviation sigma is 120 hours. Random sample n equal to 36 components that is taken. What is the probability that sample mean x bar exceeds 820 hours? That was your particular question. And your options were like this. And you have calculated that P Z greater than 1.0 is 0.1587 and you have marked T B. Okay. Now you want to know that, sir, what is the practical significance? Okay. So I'll be able to tell you. Okay. Problem is asking you for the probability that average lifespan of a sample of 36 microprocessor exceeds 820 hours. Okay. Sample of 36 microprocessors exceeds 820 hours. Individual microprocessors have a mean lifespan of 800 hours. Standard deviation is 820 hours. Means the lifespan would be somewhat 800 plus or minus 120 hours. Okay. So individual microprocessor lifetimes may be considerably lifetimes very considerably. Okay. If you are averaging 36 of them, extremely high, extremely low values cancel out each other. Sample mean X is stable and you can definitely create for the single component. N is equal to 36 is sufficiently large. Okay, that is why you shall be in a position to apply the central limit theorem. And you shall be calculating standard error, which you have done, sigma over root n, that is 20. Okay, sigma is given 120, n is given 36, root of n you have divided, you have got 20. It particularly means that sample averages 36 units typically deviate from the true population by 20 hours. So 20 hours deviation is observed in the entire population mean. Okay, that is the meaning of standard error. Okay. Now Z score normalization. Okay, measuring how far this particular 820 would be from expected mean of 800 hours. Okay, using standard error will yield you 1.0. Z score of 1.0 will indicate that sample mean of 820 hours is exactly one standard error above the average. Now you are calculating the probability using standard normal distribution table. The cumulative probability up to Z equal to 1.0 is 84.13%. Probability of exceeding this particular 820 hours in the upper tail is 15.87%. So exactly 15.87 number of components would be having a lifetime of greater than 820 and 84.13% number of components would be having a lifetime of less than 820 hours. That is the inference which we can deduce from the statistical analysis. Okay. An individual microprocessor has a decent chance of lasting over 820 hours. Okay, about 17% or 18% means 43.25% is the probability that is common. Means maintaining 820 hours average through the 36 components drops down to 15.87 because average dampens the individual outliers. Okay. In case of your quality assurance benchmark, okay, if a quality control team tests a random sample of 36 microprocessor, it will find a mean sample lifespan, finds a mean life sample lifetime greater than 820 hours. This is event which will occur 15.87% of the time. One in every 6 batch. Okay. Or two in every 12 batches. Similarly, you can calculate for 100 batches. Okay. Thus, observing a batch average of 820 hours is slightly above average, but not rare enough to conclude that the manufacturing process has fundamentally improved or changed. This you can go in your quality assurance report. Okay. Okay, this you can write in your quality assurance report that, sir, concluded, I have concluded that there is no significant improvement in the manufacturing process. Okay, that is the thing. Predictability of batch averages, the result demonstrates how statistical sampling allow engineers to establish direct confidence threshold for performance. Okay, without having the need to test the entire population of 800 or 800 for the suppose sample size of 1000 or any number of components. Any number of components need not to test it. This is the standard normal curve. This is the standard normal curve. Okay. Z equal to 0 would be here, Z minus alpha. Okay. Mu equal to 0 would be here. Mu minus alpha would be this much percentage. Mu minus 2 alpha, mu minus 3 alpha, mu minus 4 alpha, mu plus 1 alpha, mu plus 2 alpha, mu plus 3 alpha, mu plus 4 alpha. These are the individual percentages. Baseline is Z equal to 0 or 800 hours. Center of the bell curve will represent a mean lifespan of 800 hours. In standard Z score terms, mean is always at Z equal to 0. Exactly 50% of the area lies to the left of 800 hours and 50% lies to the right of 800 hours. Cumulative area up to Z equal to 1.0 or 820 hours, moving Z equal to 1.0 corresponds to a sample mean time lifetime of 820 hours. Means one standard average error you are moving means one alpha you are going forward in the right hand side direction. So the Z table value of 84.13 gives the cumulative area from the extreme left all the way up to Z equal to 1.0 means 84.13% of the sample batches of sites 36 will have mean lifespan of 120 hours of 820 hours of fuel. and just 15.87 percentage would be exceeding a lifetime of 820 years. If I spoke something incorrectly or inverse of that, okay, previously, I'm very sorry. This is the exact explanation, and I have tried to clarify things from your graphical analysis of the standard normal curves. Now, when it comes to your practical implications of your chi-square distribution, okay, I'll just explain you. Give me a minute. Just give me a minute. I'll try to draw it, give you the gist here. See, the chi-square distribution, it's a statistical analysis workhorse. Okay, it's used to analyze categorical data. Categorical data means data which is spread into various categories. So it is generally primarily used to analyze categorical data. Categorical data is that particular data that is uh, divided into different categories. Means number of columns would be there in that particular entire distribution table. So it is used to estimate how a process varies. Helps us to determine whether the observed outcome will reflect the true underlying pattern or it's a just random chance. At random, this particular event has occurred. Okay. So goodness of fish testing is there. Means what is goodness of fish testing means? It is used to check if the real world sample will try to align with the expected theoretical distribution. In case of your genetics, the biologists try to compare observed physical traits in offspring to expected the Mendelian inheritance ratios. In case of your uh, roulette wheel, which is there in your casinos, or in case of your pair of die, which is rolled, for comparing the actual frequency of numbers rolled over a wheel against the mathematical expected baseline program. That is the cases in which this particular distribution fits well. Means you are rolling a die for entire week and you are noting the probabilities or the number of chances that a particular number, suppose 1, 2, 3, 4, 5, 6 columns you have made, and it is day one, and on day one you are trying to know that how many number of times 1 is coming, 2 is coming, 3 is coming, 4 is coming. Similarly, you repeated the entire activity for 7 number of days. Okay, so you shall be in a position to have a distribution that which number will appear for more number of times. So now if you have to determine that whether there exists any statistical coherency or statistical relation that which number is coming how many number of times, or there is no statistical coherence. So for that particular purpose, this particular chi-square distribution is particularly feasible for goodness of fit test. In case of your test of independence, yeah, whether your in case of your test of independent, it will determine if two distinct categorical variables are statistically related or comparatively independent of each other, completely independent of each other. For example, if you want to check whether your consumers preferred genre of music is independent of their geographical region or dependent of their geographical region. Okay. Or, for example, in case of your doctors trying to test if the incidence of a specific illness is genuinely independent of your patient habits. For example, he is a smoker, drinker, or non-smoker, non-drinker. So between two different variables, you are trying to carry out statistical analysis that whether they are independent or dependent on each other. Okay. In case of your quality control and your variance analysis, suppose a factory is producing airplane engine parts, it will use chi-square distribution to ensure that the physical variation between component dimensions does not strict does not exceed the strict mechanical safety limits. Means it is used to establish confident intervals for a population variance, which is critical when consistency is just important as the average outcome. In case of your pharmaceutical industry, regulators can ensure the concentration of active ingredients in the manufactured products does not fluctuate beyond a precise given value. Whether and this particular concept is also used in machine learning also. Okay, model which is trying to predict loan defaults, for example. Chi-square distribution will rank the categorical variables like the marital status, educational status. Okay, and it will try to correlate that how strongly they are correlated with their default income. Okay. So this is the practical implication. In case of your testing, in case of your testing of any software, okay, comparison whether the users are exposed to a particular checkout flow, okay, or checkout flow B, or which is the exact pattern which they are trying to follow. In all those particular cases, chi-square distribution is used. That is a practical implication. Okay. Here we can use just an example. Okay, we can use this particular model to model the volatility of manufacturing tolerances. I already told you. If a CNC machine's vibration is suddenly increasing, okay, how much is we shall allow it to increase so that it does not affect the tolerance of the component it is manufacturing. Okay. So this is the practical implication of chi-square distribution. If any particular doubt is there, feel free to go ahead. Yes, we can move forward with the question. If a continuous random variable x follows a chi-square distribution with new degrees of freedom, what is the expected value of x, ex in variance x? Okay. So I have already covered very easily. You would be able to tick just it's a bonus question. If you know it, then very easily you would be able to solve it. We would see. Yeah, C would be the correct option. Very good. C, chi-square with new degrees of freedom or f degrees of freedom is the sum of f squared, okay, standard normal variables. A single z square expected value of z square is 1, variance of z square is 2. Summing f independent terms, it would be mu times 1 means f into 1. Okay, that is f or mu. Variance would be 2 times f. Okay, that is 2 of f. So as the sample size grows, both the expected value and the predictability, okay, they grow. Okay, so expected value would be having variation y equal to x or y equal to mu, but this would be unpredictability or variance would be y equal to 2 times mu. So that is the case in case of the transfer distribution. Now we try to do this question when evaluating a small sample of experimental prototypes n is less than 13, that condition has been given to you where the true population variance sigma square is unknown, that is already given you. Which distribution must be used to calculate probabilities for the sample? Try to answer this particular question.
Sir, sir, one question in previous question.
Yeah.
Uh, Sir, actually, degrees of freedom is based on the sample or else population. If you taken population means capital N, if you taken sample means n minus one. We are keeping. But
Yeah. Mhm.
madam is telling V is the degrees of freedom. But how we will be the variance and the mean?
Sorry, please repeat the last part. I'm not able to listen it properly.
Actually, in class, madam told
Uh-huh.
B is the degrees of freedom.
Okay.
So
Uh-huh.
if mean is equal to V and variance is equal to 2V,
Uh-huh.
it is derived, okay, but actually V is called a degrees of freedom.
Yeah, V is called degrees of freedom. So V or mu is called degrees of freedom. What exactly is the conflict? Don't
How
hesitate.
degree?
Speak freely. Don't hesitate. Speak freely. Speak in detail.
Sorry if I'm wrong. If I'm wrong, means correct me, sir.
No, no, no. If you are wrong, I'll correct you. No problem. But tell in detail what you are thinking. Then only I'll be able to analyze it. If you were in
Yes,
front of
sir, first.
me, then it would be much better. I would have guessed. Yeah, please repeat.
Okay,
Mm.
sir. Actually, degrees of freedom based on the sampling or population we are using.
Yes, yes,
But here V is called. We are telling it degrees of freedom.
yes.
Then how degrees of freedom will become a mean and degrees of freedom into 2 is equal to 2V, then how it will become a variance in
Oh,
chi-square.
okay,
Chi-square, you're telling all the positive values will be there. There is no negative value in chi-square distribution.
okay.
Why? Because we are
Yeah.
predicting whether the our value is within the limit 95 degrees interval or not.
Mhm.
But why this terminology scheme I'm not understanding, sir, actually.
Oh, okay, no problem. Mm.
First, why we taking degrees of freedom, sir, actually? That is n minus 1 in what is by hearted we are with the intermediate, but why we are using, I don't know.
No, no, not by heart. Nothing is done by heart. It is done by mind. Heart is just a muscle. Nothing is done by heart, it is done by mind. I'll tell you, no
Deg-
problem. I'll try to drive and show you how it came, how it became two new, then new. Everything I'll try to show. No, no worries.
Sir, actually, in degrees of freedom, n minus one is the thing, but the samples will move freely across the population,
Mhm.
and if sigma if sigma means capital N, we can't move the sample. It is a standard population, so that's why we taken all the value of n.
Okay.
Wrong.
No, no. I actually didn't listen because these are the concepts which you have made on your understanding. No problem. I'll try to sort it out. Don't worry. Keep it for the last. I'll try to show you how to F or F came. Actually, this is a just doubt solving session, so I am bound to think that you have gone through the lectures and everything is well understood, and I am just here to solve the doubts. So this is my limitation that I have been only provided 2 hours. Otherwise, I can prove everything analytically, no problem is there. But I will try my level best. Just give me some moments, I'll prepare or try to derive it and then show you. No problem. Moving forward. I understood that you are having a particular confusion in understanding chi-square distribution. No problem. I'll try to solve it. I'll try to show you that how it F, 2F or 1, 2, how it all came. No problem. So in this particular question, you shall be in a position that select correct option would be student's t distribution only. Okay. Formula selection is this one, x bar minus mu divided by s over root n. We must estimate the sigma using the sample standard deviation s. We introduce an additional layer of random variability into the ground. This forces the mathematical distribution to have fatter tails than rather than the standard normal distribution. When you are testing early stage designs, the population variance is always a mystery. Okay. Math forces it to have a wider margin, but so gradually they are converted to flatter tails. Okay. As soon as you are confident with the prototypes. That is what we have to do. Regarding question number 6, then 7, try to do it with F distribution. You are comparing the variance of component lifespans of two different manufacturing plants. Sample 1 is having N1 11, sample 2 N2 16. What are the degrees of freedom of individual uh, for evaluating the ratios S1 square divided by S2 square using the F distribution? F1 and F2 you have to calculate. Try to calculate. Very good. See here, for the F distribution, if it is follows degrees of freedoms are nu1 and nu2. Okay. So it follows a distribution s1 square divided by sigma 1 square and x2 square divided by sigma 2 square. Numerator degrees of freedom are nothing but population, sorry, sample size minus 1, and 1 minus 1, that is 11 minus 1, that is 10. And denominator degrees of freedom are 10 to minus 1, that is 16 minus 1, that is 15. So 10 and 15, they are coming. So correct option would be B only. Okay. F test is the ultimate comparative diagnostic that tells us whether a plant A is fundamentally more erratic than plant B, or if the observed differences in the simple variance are just random analysis. So this is the work of your F statistic or F test. Now you try to see here F distribution reciprocal. Okay, regarding that question is there. Because traditional statistical tables only provide right-tailed areas of F distribution, which mathematical identity correctly describes the reciprocal property used to find the left-tailed or the left tail or the lower critical values. Okay. You try to resolve. C. Good. It is not correct. I think C is not correct. Once again. The correct option would be this one. Okay. The correct option would be this one. F1 minus alpha nu1 nu2 equal to F of alpha nu2 nu1 in bracket close. Okay. The reciprocal identity. Okay. Left tail critical value is the exact reciprocal of the right tail critical value with swapped degrees of freedom. One would be having alpha degrees of freedom, then the another one would be having 1 minus alpha degrees of freedom. Alpha and 1 minus alpha. And reciprocal of the individual value. That would be there. In case of your reliability analysis, it's like the lens swap. Okay, asking if machine A's variance is significantly smaller than machine B's is mathematically identical to asking if machine B's variance is significantly larger than machine A's. So that is the analogy or which you can find out. Okay. Nothing much news there. Try this one. The production batch of 100 sensors has a true underlying defect rate of equal to 0.04. What is the standard error of the sample proportion P hat? What is the standard error you have to find? Defect rate has been given.
So in the last question, that is, we have right idea we need to transform right to left
Mhm.
guys adjectable, but we can do one minus means why we are doing reciprocal.
Your voice is not clear. Please repeat.
Sir, actually,
Uh-huh.
in Z in normal table, wherever we are doing 1 minus that value we are doing, then we
Uh-huh.
will get the opposite.
Uh-huh.
But here, we are doing 1 by reciprocal we are doing here.
So this is the mathematical identity. No? There is proof of that also. That is the mathematical identity. In Z distribution, you are talking absolutely fine. The concept regarding Z distribution is something else. This is F distribution. Okay. In case of F distribution, you have to do the reciprocal. Okay. Reciprocal and the degrees of freedom would be zero. Okay. That is the case here.
Okay. Okay, got it. That means here two distributions are there, so that's why. Okay, okay, got it. Two different distributions.
Okay, good. Very good. Okay, good. What is the standard error? Okay, that has been asked. A production batch of 100 sensors has a true underlying defect rate of p equal to 0.04. What is the standard error of sample proportion period? So standard error is given like this: p in bracket 1 minus p divided by n. P is 0.04, 1 minus p is 0.96 divided by 100, and square root of this term we will calculating 1.96 plus 0.0. This one will be correct. 0.0196 to option 1. Because defective components follow a binomial distribution, either they are pass or fail, the spread of our sample defect rate is incurred entirety by the true rate of the sample size. Variance is literally a function of mean here. Yes, directly nothing much new is there. While you putting in answer, getting is there. Then this is the thing when one population is there, sample versus truth is there, two populations are there, then two sample tree distribution is there, okay, like this. When one population is there, then if it is a known sigma, unknown sigma, then how the distribution looks. If you are going for estimating averages, you go for the Z distribution, true distribution, whether it is known standard of deviation, okay, you go for Z distribution. If it is unknown standard of deviation, small n is there, you go for T distribution, okay, for estimating averages or uh, uh, the symbol is mean one. For two populations, it is two sample T distribution. For estimating variances or the spread, you go for chi-square distribution. If it's a one population, okay, sample versus truth case. It's a two population case, we go for F distribution. Now, the final question is this one. You are testing a newly engineered composite material for aircraft stress points. You only have n equal to 8 samples. You do not know the population standard deviation, and you must estimate the mean tensile strength. Okay. Which distribution applies here? Read the question once, then answer it. Okay. Everything is given in this table only, which is just above the question. Okay, you try to answer it. Correct option, since small n is less than 30, I already told you. Okay, and you are not knowing the population standard deviation. Unknown sigma, small n means n is less than 30. You go for free distribution. Student t test. Okay. Okay, estimating mean plus unknown sigma, small n, student t. This is the formula is only the half part. Okay, selecting the right mathematical tool is the physical scenario is the true test of your expertise or how you are well versed in estimating the test statistics. Now, one simple problem was there in understanding the square distribution, how degrees of freedom is related with the mean and variance. Okay, that was your question. I will just try to give an answer to it. I try to mathematically derive it. Okay, so there is nothing no piece of difficulty is left when we try to derive things mathematically rather than understanding just the formulas or the analytics part. Just try to go with me. Suppose Zi is the this particular I is standard normal variable Zi. It follows us normal distribution n with mean 0, variance as 1. Okay. K is degrees of freedom here. Chi is the chi-square random variable. Okay. It is having k degrees of freedom. Okay. It is written like this chi-square. Okay. Having k degrees of freedom, and square is written like this. Expected value of y, expected value of a random variable y. This is written like this. Variable var and in bracket y. This is variance of random variable y defined like this: y minus e y whole square means how the particular random variable is deviating from the mean. Okay. That is expected value of y square minus expected value of y whole square. By now, you should be in a position to understand that. Okay. Fz is nothing but the PDF of standard normal distribution probability density function of the standard normal distribution. Okay. This gamma with the degrees of freedom alpha is the complete gamma function, which is defined like this 0 to infinity. Okay, definite integral t raised to power alpha minus 1 e to the power minus t. IID is independent and identically distributed. Suppose for fundamentally defining the chi-square random variable, chi-square random variable with k degrees of freedom is denoted like this: chi k whole square. It is constructed as the sum of k independent square standard normal variables. Okay. Chi follows summation I equal to 1 to k zi whole square means zi square in summation it is defined like this, where every zi follows a normal distribution with mean 0 and variance. Okay. Now you try to derive the higher ordered moment. Before computing the parameters of for x, you should define the raw moments, okay, of single normal variable z. So PDF of z is fz is 1 upon root 2 pi e to the power minus z square divided by 2, where z lies between minus infinity to plus infinity. This is the standard PDF of z distribution. First moment you try to calculate expected value of z minus infinity to infinity z into f of z. You directly try to compute this particular definite integral, you will get 0. Why? Because z is an odd function. Okay. F of minus of x is equal to minus of f of x. Okay. E to the power minus z square by 2 will be even is a uh, even function. Their product will be an odd function and symmetric integral. Okay, symmetric integral for a symmetrical interval, the definite integral from minus infinity to plus infinity would be equal to 0. So expected value of z becomes 0. Second moment you try to calculate definite integral minus infinity to plus infinity z square minus z square into f of z. That is 1 upon root 2 pi e to the power minus z square by 2 dz. By definition, variance of z is nothing but expected value z square minus expected value of z whole square. So known variance of z is 1 and expected value of z is equal to 0. So by definition, expected value of z square you will try to calculate as 1. Fourth moment, if you try to define, from here I have calculated expected value of z square. This value I have tried to calculate. Variance I already know that is equal to 1. Okay. And expected value is 0. That I already defined. Okay. That has already been defined. That variance is 1 and expected value of z or mean is 0. Okay. Normal distribution with mean 0 and variance 1. Okay. Z follows this particular distribution. That has already been defined. So here I calculated this second movement as 1. Fourth moment, again I will try to calculate 1 upon root 2 pi, then z cube, z square, z to the power 4 will come here. Okay. In case z to the power 4 will come here, okay, that I can write it like this: z cube multiplied by z into 2 to the power minus z square by 2 into dz. Now you take u as z cube, du as 3z, z square dz, try to calculate v this du dv will become z into e to the power minus z square by 2 dz, and v you take as e to the power minus z square by 2. Then using the formula you will try to compute the fourth movement. Okay, from LS hospital rule, the limiting term you try to calculate, it will come 0. Okay, and finally this particular term will be reduced to 1 and another term will vanish. This entire term will be vanishing. This will become 0 from all L hospital group. Okay, and this particular term will be getting as 1. Okay, z sorry, this particular term will be becoming 0 from LS or L hospitals room. This particular term will be splitting it. Okay, this minus minus will become plus in 3 into 1 upon root 2 pi. You can take outside the bracket z square into e to the power minus z square by 2 dz. Okay, this definite integral already calculated, that is coming 1 in the previous e to the power z expected value of z square we have tried to calculate. This is coming 3. Now, phase-wise, if you try to calculate mean and variance of the individual components zi whole square, so expected value of wi, let wi be defined as z square. So expected value of wi will be coming 1. Variance of wi would be defined like this. Okay. And phase-wise, if you will try to compare and for the entire chi-square distribution, that is nothing but the summation of zi whole square to I to k, where k is the actual degrees of freedom. Okay. So expected value of x would be 1 plus 1 plus 1, 1 to k times. That is why it is coming k. Mean is coming as k. Okay. And variance, if I am computing z as whole square, so that if I can just split like this, so it would be coming finally as 2. So that is why I have written it as chi-square follows the distribution with mean k and variance with, and this one is the entire analytical proof with why I have written that as 1,000. Okay. I'll provide you the complete notes. Okay, please go through them. And this is the very beginning of the course, and these are the very important things. Even if you don't understand reliability engineering, no problem. But as an engineer, you should understand statistics. Basic statistics is the fundamental. These distributions. That is why, in great detail, I am providing you notes so that you can revise them multiple times. These distribution, fundamental distributions, Z chi-square, T, F distribution. 4 distributions are very, very, very important. As well as binomial distribution, Poisson distribution, which we have covered in our previous lectures. If you don't understand reliability engineering, that is totally up to you, totally fine. But as an engineer, you should understand the statistics. Okay. My sincere request to you is, after the class is over, feel free to go through these all the notes. I'll provide the PDF, provide the links to the recording also. Listen, but do revise and be very, very thorough and confident. That's how degrees of freedom have come, how which concept is defined like this. Okay. And if any problem is there, feel free to contact me on the mail also. Okay. I provided the mail on also. So you can contact me. This one is the link for your notes. Okay. And mail once again I am providing you. So mail is there with you and notes are there with you as well as recordings are there with you. Feel free to go through the entire proof and entire syllabus. Okay. And be confident that whatever you are reading, it is correct. Understand it correctly, process it correctly, and afterwards, please prepare for the examination and try to score excellent marks in this particular course. Okay. Thank you once again for joining this particular session. Due to your queries only, it is extended a bit late. Sorry about that. Okay. And thank you once again for joining the session. Do join the session next week, same time, same way. Okay. Thank you all. Yes. I'm ending the meeting. Over. Thank you once again. And do join the session next week, same time, same day. Have a great day.